And we are live. Excellent. Excellent, excellent, excellent. Can you see that okay? Yeah. My light's kind of dying on me. I gotta plug that sucker in. Or something like that. Let me remove this. And see if I can't get it charged real quick. Or charged at all. Or something like that. But anyway, here we are, ladies and gentlemen. Back once again. I am at home. You are at home, I guess, or something like that. Anyway, but yeah, if you would, please leave a comment in the chat. That would be wonderful if you would go ahead and do that. We will get started in a little bit, give people an opportunity to get in. I know I was a couple of minutes late getting into this, dealing with little issues here and there. Okay, and we'll get this thing moving. Here, let me just, here, I gotta, hold on one second, I just gotta mute myself. Okay, I'm back. Just relaying message. Who's knocking at my door? I feel like this is like a Mr. Rogers Neighborhood episode where people like they knock and I'm like, I wonder who that is, and then we bring them over and then they introduce themselves and all this fun stuff and but we'll get this thing moving. What is this? Wait, what is this? We've decided to give you 3 additional What? Are you kidding me? Come on, dude. Sorry. I'm getting all these emails and it's just like, "Hey, this has been extended." Even though we told you it wouldn't be extended. That's great. Where is everybody? There's only 9 people here. 10 people here. Everyone should be leaving comments and being like, "Oh, Mr. Markey, they said it was going to snow today." I know. And I was like, "Hey, you guys are going to snow today." Yep, I love that snow outside. Can y'all see that snow outside? Because I can see that snow outside. Oh, goodness gracious. Anywho, okay. Let me see if I can't get a little better light right here. Bring this over. See if this works any better. Ooh, that's bright. That might work. Let's see if that works. I literally just brought a lamp over. Now, typically what I have is I have this device that oh, that's really weird and bright. I may have to change that. Yeah, I'll see if I can bring back the device in a minute. But typically, I have this device that attaches to magnets. Yeah, I'm totally not going to leave that light there. I apologize. What is up with that thing? Look at that. Look how terrible that is. Okay, that's not so bad. That's actually a little bit better. Let me see how it looks here. No, I don't like it. I don't like it. Move this lamp out of the way. See, that's not so bad. What if I could leave it over there? Okay, I have an idea. Give me 1 second. I'll take my headset off. Reconnection successful. Okay. Okay. I think I'm back. I'm going to post something in the Google Classroom to get people back here. I think I'm back. If I'm back and you can hear me okay, please let me know. I'll tell you exactly what happened in a moment. There we go. So, sweet. Okay. I'm going to post this then. Boost. There we go. No. It wasn't your Wi-Fi. It was me. It was all me. I'll tell you exactly what happened. So the long story short is this. Actually, no. I'm going to tell the long story. So I have this setup at home for live streaming that is really nice. And in fact, the reason why it's so nice is because I have this top-down system. Now, right now, I have literally a desk lamp lighting this right now. Typically, I have this thing. Now, this thing is really sweet. What happens is this thing has like little magnets on the end, and I can attach it up to my rig that I have my phone on because I have little magnets there. And then when I hit it, it lights up whatever I'm looking at, and with like LED lighting, and it's fantastic. And you can see everything that I'm writing, and everyone's happy and fine, and everyone high fives each other, and it's great, you know. But this is also something that my kids like to play with. Look, hold on, ready, ready, ready. My kids like to play with that for obvious reasons. And what ends up happening is I can charge it. It doesn't take batteries. I have to charge it. And when this thing dies, which I just charged it for like 5 minutes before, so it has a little bit of a charge now, but I got to charge it for like a couple hours. But yeah, it's just, it's one of those things. So anyway, I went to go fix the lighting because that lamp was too close, and I moved a chair to put the lamp on top of, and it disconnected my Wi-Fi. Thankfully, with the joys of the internet, I'm able to reconnect very quickly, as you can clearly see. And here we are. So, I do apologize for the craziness that this day has been. Again, like, we found out last night that we were going to be teaching from home. Hey, hey, look at that snow outside. Like, yeah. I swear to you, if we don't get like a couple feet of snow by the time I would have left work, I'm going to be really upset. Anyway, thank you guys for hanging out with me. Here's the goal for today. Now that I've done that whole heartwarming intro, we're reviewing Chapter 6. And the reason why we are reviewing Chapter 6 is because I am going to be assigning you a major. I'm going to have the major assigned at some point tomorrow. Yep, at some point tomorrow. And you will have the duration of the weekend to get that thing done. In fact, I'm pretty sure I'm going to have it due probably on Tuesday or something like that. That would be fantastic. There we go. Just fixing my chair. Yeah. I'm just trying to see if there was anything else before I get to my final announcement. We're going to be reviewing the chapter. I'm going to be posting something for that. I'll talk about that. Okay. Before we get started, a couple of things. Number one, yes, there is a homework assignment out there. Make sure you get that homework assignment done. It's on Google Classroom. But more importantly, this. Next week, I get kids back in my classroom, and I get to see you again. I have you Monday, Wednesday, Friday. I'm giving you the heads up today, and I'm going to remind you on Monday. On Wednesday, I will not be in school. I don't know what they're doing in terms of a substitute. I've already put in for the day, but I have things to take care of. For those of you that are in class, obviously they'll have the attendance taken care of for you there. For those of you that are online, what's going to happen is that since they're not going to, connect with you online because they don't have access to my Google Classroom, I'm going to leave an assignment scheduled to be released in Google Classroom for that particular day. It's going to be released to when the class period begins, and your attendance is going to count as having done that assignment, basically. And we'll go from there. Yay. Okay. So right now, I am going to post in the Google Classroom a PDF that we are going to work on today. And this PDF is going to be the chapter review in preparation for this major. If you have any questions in regards to it, as we are moving along with these problems, please, by all means, ask those questions. I can see y'all in the chat right now. You're all right there. It's fantastic. But I would like to review this. So, there we go. go. Let me open up that PDF on my screen. I don't want to open up with Google Docs. I want to open it up with Lumen PDF. There we go. So obviously, if you want to see it for yourself on your computer, you have it right there. Otherwise, no, I don't want to search. How do I zoom in here? Here we go. There we go. Nice. And I'm going to flip my screen over so you can see that as well. No, not that website. I want... Where are you? That one! No, not that one. I thought I deleted you. That one? No, that one. There we go. I nailed it. There's the review that we're going to be working on today. So, oh, happy day. Happy day. Okay. Now, I'm not going to do every question, but I am going to be doing a majority of them. So keep that in mind. If you do not already have them out, I'm going to need those notebooks out and open. Okay. So first things first, I'm going to write down some information in regards to numbers, well, technically numbers 1, 2, and 3, I guess you could say. And then I'll flip my camera over so you can see it. On number 1, they have the function written, well, I'm literally writing it exactly as they have it. I'm not writing down every word, I'm just writing down the information that I need. And I want to talk about the difference between this question and number 3. So go back to top down, there we go. There's the information for problem number 1. Now, there's a huge difference between problem number 1 and problem number 3. And that difference being the symbol that they use. The symbol that they use on number 1 obviously is a dot. It's a solid dot. That focus, yeah, it's focusing back. There we go. Whereas if you go to number 3, if you look right there on number 3, there is a little open circle on number 3. Those two symbols mean completely different things in the realms of this problem. Number 1 is asking for multiplication. Number 3 is asking for that operation that I taught you in this chapter known as composition. Composition was the act of taking one equation and shoving it inside of another equation. But on number 1, there is a single solitary dot, so we have to deal with a multiplication. So here we go. I got to multiply these two things together. And I think, personally, the absolute easiest way of going about multiplying these together is by creating a little 2x2 box. You plug in the stuff and you multiply it out. I don't know why I changed my accent there. That was weird. Well, the reason why I know it's multiplication is because of that dot. The reason why I'm creating a little box is because this is a binomial and a binomial. Keep in mind the negative is on the x. If I multiply this out, I'm going to get 7x squared. I'm going to get a 28. I'm going to get a, negative x cubed. And then a negative 4x. Be careful on that box right there. Be careful. You are multiplying. And then those magic words, when you combine like terms, however, there are no like terms. You have to have the same variable and the same exponent to get that thing done. So we got negative x cubed plus 7x squared minus 4x plus a 28. Yeah, that is the simplified answer when you multiply these two things together. Wunderbar. If I go back to the problem, now number 2 and number 3, I mentioned number 3 before, but number 2 and number 3 are actually dealing with composition. I wonder, I'm in this little box down here. I don't know, whatever. Anyway, let me get a piece of paper. I got all my stuff right here. Here we go. and then I'll show you what I'm writing in a moment. I wonder, can I actually get the top-down thing there? What did I call it? I called it webcam? No, that's the webcam. And then my top-down is my phone. I wonder if I could do both at the same time. Top-down is my phone. Right. It's a window capture of my phone, which I can have right here now. Look at me! Look at me doing stuff. I'm right. I'm starting down right here. Oh, technology. Okay, so you can kind of see what I'm writing, and I can zoom in on this if need be. So here we go. Let's talk about number 2. This is so awesome. Sorry, I just think this is the coolest thing ever. Anyway, so they change f of x and g of x. They say f of x is x minus 5, and they say g of x is x squared plus 3. Look at that. But now they actually want you to perform the composition, and they want you to perform f of g of negative 2. Look at me go. Now this is a composition. It's just in a different way of looking at it. A composition function is one function literally shoved inside of another function. In fact, when you are evaluating problems like this, they really want you to evaluate the inside first, just like we typically would using PEMDAS, inside out, when you are evaluating expressions. Not solving, evaluating. So I'm going to figure out g of negative 2. G of negative 2, if you evaluated this correctly, should give you 7. Yeah, should give you 7. Good for it. G of negative 2 is equal to 7. Wait a minute. G of negative 2 is equal to 7. G of negative 2 is what was inside of here. Since it's equal to 7, I'm just going to plug that 7 in. Cool. So f of x was really x minus 5, so f of 7 should be 7 minus 5, which is 2. That's one way of looking at a composition function. There's always more than one way of doing a problem like that. There's absolutely more than one way of doing a problem like that. But that's probably the most straightforward way of doing that problem. But now number 3. Number 3 doesn't give you a number to plug in. Number 3 literally wants you to complete the composition. Once again, changing the value or the, what f of x and g of x are programmed to do. Thankfully, they gave you a nice one. In this problem, they want you to do f, that symbol g. That's f of g of x. That's what they really want. F of g of x. That's what that symbol is. Another way of writing that is f of g of x. That's another way of looking at it. And you can see the g of x being on the inside of that function. G of x is going inside the f of x function. Inside the f of x function. Notice what I just did right there. Inside the f of x function. The f of x function is the outer layer. The f of x function is the outer shell. I can take that g of x, shove it inside, and now all I have to do is simplify. So, distribute. I get a 2x squared minus 6 plus 5, and a 2x squared minus 1. That would be the simplified composition. That's how composition problems work. You typically take one function and shove it unwillingly inside of another function. Weird. So, let's talk about number 4. Number 4 takes it in a slightly different direction. Number 4 is talking about inverse functions. To bring you back to the idea of inverse functions means that we talk about the three properties that inverse functions had. Number one, if you were to graph them, which they're not asking you to do here, but if you had to graph them, then they would look like reflections of each other. In fact, I could probably bring that up on Desmos. I want to bring up. Here we go. Hold on. I could bring that up here. Yeah. Let me bring up Desmos here. Desmos graphing. And let me do f of x equals x squared, and f of x equals, let me do the square root of x. And just for the fun of it, f of x, probably shouldn't really be doing f of x, but whatever, equals negative square root of x. In fact, I probably do h and g, so let me do h here and g here just for the fun of it. Cool. Now, I can't see what I'm doing here, so let me move this up a little. There we go. Now, what you see here are two functions that are reflections of one another. They're reflections of one another. And the reason why I know they're reflections of one another, specifically across the line y equals x, is because y equals x cuts it right down the middle. It's a diagonal, and if you were to fold them in on each other, they would lie right on top of each other. That's one property of inverses, that they are reflections of each other across the line y equals x. The second property is that every single ordered pair x comma y is actually y comma x in the inverse. For example, if we were to plug something into this function right here, like a 2, no, like a 4, yeah. You plug a 4 in for f of x, boom, and it spits out 16. But then when I go to g of x, if I actually plug in the 16, I get 4. Because every single x comma y becomes y comma x in the inverse. Then, let me actually flip this back here. There we go. And there we go. Then, what ends up happening with the inverse is that if you took a composition, which is what we did in 2 and 3, but if you took a composition of them, it would result in x. Number 4 wants you to find the inverse of this. Inverse, meaning what is that function that it would be reflected across y equals x. What is the function where every single x comma y becomes y comma x? What is the function where if you took the composition of them it would result in an x? Well, there was a process that we went through. Typically, I'd like to write it like y equals, and then I would like to utilize the second property of inverses, which would be every xy is yx in the inverse. Literally just switching the x and y, because now I have performed the inverse step. That is the inverse step. All I have to do from here is solve for y. Now, I am going to divide by 5, which it would give me a 1x over 5, but I decided to write it as a 1/5 x. Same thing. And technically, if you wanted to use the proper notation for inverses, this is what it would be. Oh, I hear noise at the door. I wonder if that's my son or daughter. They're just banging at the door. You can let her over for a minute. Let her over for a minute. Okay. Hold on. Hold on, everyone. Come here. Come here. Step over. Oh, here we are. You want to say hi to everyone now? Here we go. You say good morning. Yeah. Are you sleepy still? Yeah. What are you doing? You don't know? Yeah. What'd you eat for breakfast? Pancakes.
No, I want rainbow pancakes.
Rainbow pancakes. Wonderful. Okay, well, Daddy's going to get back to work now, okay? Okay, can you say goodbye to everyone? No, you got to look at the computer and say goodbye. There she goes. She's waving to you. Okay. Bye-bye. Okay. Oh, goodness. Those pants are falling. All right, go with Mom. I'm very mad at all of you now for not commenting on how cute she is. That is incredibly upsetting to me that none of you, well, Lindsay did. Lindsay gets a gold star, but the rest of you get nothing. Nothing. Anyway, back to this. Okay. Oops. Oh, goodness, what is wrong with me? Lots of stuff. Okay. Let's talk about number 5 then. Okay. Okay, number 5. Number 5 wants you to determine whether or not they are inverses of each other. Well, once again, I'm going to utilize one of those properties. I could graph them. I don't want to. If I want to determine whether or not they are inverses of each other, I am actually going to put one function inside of the other. I'm actually going to prove that they are inverses of each other, because the answer would either be yes they are or no they're not. And the way that we determine that is by taking the composition function. And if the result of the composition function is just x, then yes, they are inverses of each other. Phenomenal. The outer shell is f of x. As you can see right there, there's the outer shell, 5x minus 3. But that x will now be replaced with an x plus 3 over 5. And now all I have to do is simplify. The 5's cancel, leaving me with x plus 3 minus 3, and I am just left with an x. So, yes, they are inverses of each other. Haha. Take a sip of my coffee. That was great. Okay. I'm going to speed this along just a little bit and show you what you can do with something like number 6. Now with number 6, they want you to graph that. And they want you to state the domain and range. In terms of graphing that thing, obviously you have graphing calculators. But I do expect a little bit of accuracy. And what I mean by that is this. You have your graphing calculator. Just fantastic. Good for you. Let me actually flip to the top down so you can see that a little bit better. There we go. If I go to my, let me reset this. If I go to my y equals key, and I type in the square root of 2x minus 8, fantastic, whatever. I could graph it. I'm like, oh, look, there it is. Good for you. I need a little bit of accuracy here. I need to know where these ordered pairs are. I need to know an accurate accounting of this. So, you need to get a table of values. But this table of values, you don't need every single ordered pair. You just need the appropriate ordered pairs. Now, if you notice for this thing, I get a bunch of errors. Again, this was the, y equals the square root of 2x minus 8. I can't have a square root of a negative and graph that. I can't do that, which is why I'm getting all these errors right here. See that right there. In fact, the first ordered pair is 4, 0. And now that 4 comma 0 should actually make sense as a starting point. Because typically, this thing would be like a times the square root of x minus h plus k. If you notice, there's no plus k there. There's no plus k in the equation. So you can assume it's a plus 0. H comma k represent the starting point. If the k is a 0, then the starting point must have a y value of 0. So where'd the 4 come from? Well, if you take that equation, 2x minus 8, set it equal to 0 and solve, you get positive 4. So now in terms of ordered pairs, I am not going to write down all these decimals. I'm going to write down 4 comma 0. I'm going to write down 6 comma 2. And I'll probably write down 12 comma 4. Yeah. 4 comma 0, 6 comma 2, 12 comma 4. Those would be appropriate in terms of graphing this thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4. 4 comma 0. 6 comma 2. 12 comma 4. And you can see that curve. There it is. I need a bit of accuracy. And that accuracy is going to be from the ordered pairs that you get. You don't have to do the decimals, but I do expect those whole numbers to show up when you graph it. If you want to talk domain and range, domain goes from the starting x value all the way to the right, how far left and right the graph goes. The range is how far up and down it goes. It goes down to a y value of 0. That's where it starts. And it's technically going up to infinity. Crazy problem. Okay. Let me flip back to here. And let me scroll down. I'm number 7. I'm going to have you cross out number 7. I'm not assessing you on number 7, so don't worry about that. You can also cross out number 11. Number 11 is not something I'm going to be covering on this major assessment, so you can pretty much skip that as well. But let's talk about 8, 9, and 10. So number 7 cross out, number 11 cross out. Let's see. But I'm going to be doing 8, 9, 10 right now. I'll probably write this down and then flip to see the camera better. And we'll see. You can probably see this, but whatever. Number 8. The square root of 4 over 49. Now, technically, you are not allowed to have a radical in the bottom of the fraction. And you're going to see that on a problem we do later on. But yeah, you're not allowed to have a radical in the denominator. You can't, unfortunately. Oh, wait. Hold on. 49. Can I do this? And the answer is yes. Yes, you can. You can do that. The square root of 49, obviously, is a perfect square. So is 4. So something ends up working out quite nicely for you. But the reason why I am allowed to do something like that is because there's only multiplication or division on the inside of the problem. That's the only reason I'm allowed to do that. If there were adding or subtracting, couldn't do it. Multiplication, division, heck yeah. There's the answer. I guess that radical took care of itself. Anyway, take a condescending sip of my coffee. Anyway, back to this. Number 9. Number 9 is another 49 in there. The square root of 49, x to the 6th, y to the 4th. Now, there are a number of ways to get this done. Right off the bat, there's only multiplication. So you could split them all up to their own separate radicals. Is a square root. Square root of 49 is 7. I mean, like, we're rolling with this thing. You could split up that x to the 6th to be like, what, x squared, x squared, x squared. And that y to the 4th is y squared, y squared. And basically everything escapes. Everything escapes the radical. Cool. You could also do it like this. If you happen to remember, I'm showing you an alternate way. But if you happen to remember power over root, it's a square root. Power over root. I can distribute this exponent. Mr. Markey, I thought you couldn't distribute exponents. Yes, you can, as long as there's only multiplication or division separating those terms. Power of a power, you multiply the exponents together. 2 times 1/2 just gives you 7. 6 times 1/2 gives you a 3. 4 times 1/2 gives you a 2. That's called a shortcut. But the only reason why this shortcut works is because every exponent would simplify nicely or be divided by 2. That's the only reason why it worked. The only reason. If one of these exponents were like a 3, it may not work nicely. In fact, I couldn't do this method with the next problem. I couldn't with the next problem. With the next problem, I'm going to do the old method because it actually works out quite a lot nicer. The third root of 24, a to the 6th, b to the 5th. Now the thing is, that's a 5. Now the thing is, that's a 5. There we go. Sorry. The 24 is not a perfect cube. 24 is not a perfect cube. 5 can't be divided by 3. So what do? Well, it doesn't take that long to figure out that 24 could be broken up into the following. 24 can be broken up into 2. I can't say 2 times 2 times 2 times 3, which is 8 times 3. 2 cubed times 3 to the 1st. That's what 24 is. Break it down as far as it can go. A to the 6th is really a cubed and a cubed. And b to the 5th is really b cubed, b squared. Because that's b to the 5th. This is the old method. This is the tried and true method. This is the method that works. This 2 can escape. This a can escape. And this b can escape. 2a squared b, those were allowed to escape. And unfortunately, that extra 3 and that b squared are stuck. There's nothing you can do. That's a really loud noise, but there's nothing you can do. That's as much as you can do. It looks terrible. It looks worse than the original, but that is the simplified form. Weird. All right, let's go to the next page. Now, like I said, there are a few problems back here that I'm not going to do. I'm not going to do number 16. And I'm not going to do the bonus. I will skip number 12 for now. Keep in mind, number 12 was fair game. Number 12 was fair game, but I'm skipping it for now because I'm going to do the other word problem to review with you guys. So for right now, I'm going to skip to number 13. I see you there. Sorry, I just see the comment pop up in the chat. I'm like, okay, yeah. Let's see. I was going to give the reminder at the end of the stream if people hadn't commented to leave a comment. You know. All right, number 13. Number 13 gives you the fifth root of 32m cubed. I'm gonna have to change markers soon. This marker's dying. I got a box here somewhere. You know what? Yeah, I'm gonna switch it now. I like this box better. There we go. Now this problem is asking us to write the radical using rational exponents. What are rational exponents? Well, rational exponents are fractions. They're fractions. Okay. Power over root fractions. Okay. Power over root fractions. Technically, this problem's not asking for you to simplify. It's asking for you to write it using rational exponents. One way of doing that is, okay, power over root. Is that it? Yeah, it kind of is. It is. Technically, that would be sufficient for answering the question, because the question did not ask you to simplify, it just asked you to write it using rational exponents. Phenomenal. I can take this problem a little bit deeper, though. There is more than one way to write this answer. That's one way of writing it. I'll write it right there. Here's another way. Another way of thinking about this problem is recognizing the fact that this 32, and it doesn't take that long to figure out, is actually 2 to the 5th power. It is. And because it's 2 to the 5th power, it can technically escape that radical, 2 5th root of m cubed. But that still doesn't answer the question, because the question wanted rational exponents, meaning a fractional exponent. These two answers are technically exactly the same. They are saying the exact same thing. They're just written in different ways. They both have the fractional exponent that the problem wanted. It's just that I took one a little bit farther than the other. But they're the same thing. Weird. Let's look at number 14. Sorry, I keep doing the eyebrow thing. Anyway, number 14 wants you to simplify the following. There we go. I'm going to go back to top down for this one. There we go. See it a little bit better. Focus that camera in. Come on, focus that camera in. There we go, better. They want you to simplify this. Thing is, all of these bases are being separated by multiplication division. All of them. And since they're being separated by multiplication division, we can technically combine all of them using our exponent properties. But, typically we would combine them if they had the same root. Power over root. The root is the denominator on the fraction. Oh man, I'm going to need common denominators here. Oh, snap. If I make them common denominators, technically, they would all have a 6th root on them. In order to combine them, they all have to have the same root. They all have to have the same denominator on the fraction. The exponent properties that we learned at the beginning of this chapter basically stated that if you wanted to combine these, you would either have to add or subtract their exponents together. Well, if you add or subtract fractions, you need common denominators. When you multiply common bases, technically you add their exponents, and when you divide, you subtract. This really should be 6 minus 6, or 6 over 6, I should say, minus 3 over 6, minus 2 over 6 as the exponent. That is actually the answer. Again, 6 over 6 minus 3 over 6 minus 2 over 6. 6 minus 3 minus 2 gives you 1. The denominator stays the same. The concept of common denominators and roots or radicals are very similar. They work very cohesively together. Flip back to here. There we go. Ooh, I'm also going to be skipping 16. Don't worry about 16. 16 is not something I'm going to worry about on this major assessment that I have for you. But let's talk about number 15. Number 15 is the cubed root of 3m plus 1 equals 4. This is what we've been working on for the past week or two, week and a half. Getting the variable by itself, solving for the variable, peeling off the outer layers. One thing you absolutely have to know, there are parentheses around that 3m plus 1. And if there are parentheses around that 3m plus 1, then according to SAD/MEP, you deal with parentheses last. There's no outside addition subtraction. There's no outside multiplication division. So the first thing I got to do is cube both sides. If I cube the left side, the radical goes away and the parentheses drop off because now I'm inside the radical. And if I cube the right side, I get 64. 64, 4 cubed, I should say, 64. Now you're back in pre-algebra. Subtract 1, divide by 3. Divide by 3. 21. Nice. You must always check for extraneous solutions. You can check by simply just plugging that number back into the original and seeing if it works. 3 times 21, 63. 63 plus 1, 64. Cubed root of 64, not the square root, the cubed root of 64 is 4. And it works. Yay! Okay. Couple more problems here. Number 20 is also fair game, but I'm going to deal with that through number 17, just because it's a word problem. I would definitely like to get done at least number 17 and 18. Number 19 is fair game as well, but we've already done a problem similar to that. So I'm going to wrap up with 17 and 18 today. Yeah, I'm going to wrap up with 17 and 18 today, just so everyone is on the same page here. There we go. So let's see, 17. Now 17, you're going to have to be very careful. I know y'all hate word problems. I love them, but y'all hate them. The velocity of v in feet per second of a roller coaster at the bottom of a hill is related to the vertical drop h in feet. Mr. Archie, why are you making us do this question? If feet per second of the coaster at the top of the hill, the formula. Mr. I hate word problems. You lost me at the word velocity. What velocity must the coaster have at the top of the 100 feet? I can't believe you're making us do this. To achieve a velocity of 100 feet per second. Oh my gosh, I completely checked out. That's how y'all sound. Now, you have to break this thing down piece by piece. There are 3 variables in that equation. Number 17. V sub 0, V, and H. Break it down piece by piece. Let's focus on V, because that's the first thing they tell us. The velocity V of a roller coaster at the bottom of the hill. Okay, hold on. V is velocity at bottom. Okay, that's what I got from the first sentence. V is the velocity at the bottom. H is the drop. Okay. V sub 0 is the velocity at the top. Okay, so let's think about this logically for a moment. You're going down a roller coaster. Whee! Like that. There is a certain velocity at the top. There is a certain height, which represents the drop. And there is a velocity that you have at the bottom. Just trying to conceptualize what this problem is telling me. What velocity must a coaster have at the top? Meaning, V sub 0 is unknown in this problem. At the top of a 150-foot hill, that must be the drop, to achieve a velocity of 100 feet per second. If they're asking me what is the velocity at the top, that must mean that 100 feet per second represents the velocity at the bottom, and 150 must represent the height. V sub 0 equals 100 squared minus 64 times 150. This is the proper way to do the problem. If you break it down piece by piece, you can get this thing done. Break out my calculator here, change it to top down so you can see it a little bit better. Square root of 100 squared minus 64 times 150. 20. Right on the dot. V sub 0 should equal 20 feet per second. Yep, feet per second. And that should make sense in terms of roller coasters, because obviously at the top of the hill you're kind of going a little slower, and then you gain all that velocity going down the hill. So you're at 20 feet per second at the top, and then you drop 150 feet, and then you achieve 100 feet per second at the bottom of the hill. That's the interesting thing about roller coasters. Roller coasters, originally, what they were intended to do was they didn't actually give you velocity. They had the little track thing that brought you all the way to the top of the hill, and then you were like down the hill, and then all that velocity that you gained was the only velocity that you had. Which is why roller coasters have like the twists and turns to kind of build your inertia. But yeah, you're pretty much freewheeling at that point. Like there's nothing speeding you up or slowing you down until the end. It's actually really interesting, the physics behind roller coasters and how they work. But I digress. Last problem, number 18. They want to know what is the square root of 34 when divided by the square root of 51. Now I've told you, you can't have a radical in the denominator. But let's see what we can simplify. Trust me when I tell you that 34 can be broken up to be 2 times 17. It doesn't take that long to figure out. And 51 is 3 times 17. Now, what's really nice about that, Miss Markey, can I cross out those 17s? Well, not only that, you can cross out the square roots of 17. They cancel each other out because they're only separated by multiplication and division. Typically, if you want to take a very nice step here, there has to be multiplication division separating these things. That's usually the case. But we're not done yet, because I got the square root of 2 over the square root of 3, and I can't have a denominator in the bottom of the fraction. I'm sorry, a denominator, a radical. I can't have a radical in the bottom of the fraction. So what do I do? Well, what you must do is this. You must cancel out that square root in the bottom. But you can't change the value of that fraction. That fraction has a certain value, a decimal number, so to speak. And you can't just be like, well, I'm just going to make it 2 over 3. No, can't do that. In order to cancel out that radical in the bottom, the best way of going about it is multiplying it by 1. Look, right here. I multiplied by 1. Root 3 over root 3. Look, I'll prove it to you. Watch this, watch this. The square root of 2 divided by the square root of 3 is actually this decimal right here. And if I take that decimal and I multiply it by the square root of 3 divided by the square root of 3, I'm not changing the value, here, top down, I'm not changing the value of that decimal. The same decimal, I'm multiplying it by 1. See? So, the reason why I do this is because now, when you multiply something by itself, you can square it. Or more importantly, you can bring those together to be the square root of 9. Square root of 3, square root of 3, multiplied, square root of 9. 2 and 3 on top make it 6. That is the proper answer to this problem. Same exact decimal. If you have not gotten done that assignment in Google Classroom, please make sure that you do that page out of the book. Tomorrow, I am going to be assigning you a major on Google Classroom that you will get done over the course of the weekend. It will most likely be due on Tuesday, so I will remind you on Monday. Please do not leave it for the last minute. If you have any questions, email me. If you have not left a comment in the chat, please make sure that you do that. I'm going to sign off. You guys have a wonderful day. Woo! I don't know. Just going to kind of sip my coffee and kind of take a sip back. Okay, that's it.